Good evening everyone, good evening. I welcome you all again back to NEET Elite. I hope you guys are doing great, having a good time. Well people, you can let me know in the chat box if I'm audible and visible to everyone. Yes, just let me know in the chat box with some thumbs ups if I'm audible and visible to everyone. Hello Harsh, hi Dayanand, hello Bibek, hello Ishpreet, hello Shiva, hi Anish. Hi Shivam, hello Basit, hello Uzair, hi Hemant. Welcome everyone, welcome back. Hello Aleem, hi Dayanand, hi Anish, hello Shaukat, hi Monisha. Welcome everyone, welcome. Thank you Shiva. I'm doing good, how are you? Perfect guys, perfect. So just let me know in the chat box, give me some green signal from the chat box so that I'll get to know whether I'm audible and visible to you guys or not. Yes, so that we can start the session directly without wasting a lot of time. Yes? Let me know fast in the chat box. Let me know fast in the chat box, yeah? Perfect guys, perfect. So as you all must be knowing, tonight we are going to start something called as de Broglie Hypothesis, and with this de Broglie Hypothesis we'll talk about something called as Heisenberg's uncertainty principle as well, right? Basically we are going to cover two topics in the today's session. One is going to be your de Broglie hypothesis and the second one is going to be what? That's something which we call as Heisenberg's uncertainty principle. Okay, these are the topics which I'll be covering right here in today's discussion. So people, before starting the session, the ones who are new to the channel, let me introduce myself. My name is Wassim Sir and I'm your chemistry master teacher right here on this NEET Elite channel. Yeah. The ones who have not liked the video yet, please and please do like the video. Share the video with your friends and do not forget to subscribe to the channel and do not forget to hit the bell icon so that you get the notification of every single session which will be taking live on this NEET Elite channel. Yeah. So people, you can let me know in the chat box if you guys are super duper excited about this session. Let me know in the chat box with some thumbs ups, right? Let me know fast in the chat box if you guys are super duper excited about this session. Ishpreet, my throat is in a better condition, yeah. Let me know in the chat box if you guys are super duper excited about this session, yeah. No Monisha, this is not going to be the last session. After this session, there will be 3 more extra sessions from this chapter, okay. In the next session, basically we are going to enter into the quantum mechanical part. Yes, we'll be talking about something called as Schrodinger's wave equation. We'll be doing the quantum numbers, electronic configuration, everything will be covered here, yeah. Perfect. So let's get started guys, let's get started, let's not waste a lot of time. Let's get started with something called as de Broglie's hypothesis, right? What is this de Broglie's hypothesis all about? Okay, well people, all of you would be knowing about something called as light, yes? Okay, as you all must be knowing, the light, we say it has got the dual nature, right? Light has got the dual nature. That means light, it behaves as the particle and at the same time it can behave as the wave as well. What does that mean? That means some of the phenomena of light are explained by considering light having the particle nature, yes, and some of the phenomena of light are explained by considering the light to be having the wave nature. So we say light has got the dual nature, it has got the wave nature as well as particle nature. Some of the phenomena shown by light are explained by considering light to have the particle nature, and some of the phenomena shown by light are explained by considering the light to have wave nature. All of you must be knowing about this, right? We know it. We have discussed this as well. Light has got the dual nature, that's wave nature as well as particle nature. Some of the phenomena shown by the light are explained by considering the light to have the wave nature, and some of the phenomena shown by the light are explained by considering the light to have the particle nature, right? In the similar way, what de Broglie said, what was de Broglie's hypothesis all about? Whatever matter we have around us, as per your de Broglie's hypothesis concerned, whatever matter we have around us, everything, be it electron, be it proton, be it photon, whatever we have around us, everything possesses the duality. everything around us, it possesses what? It possesses something called as duality. That means everything possesses the wave nature as well as particle nature. Everything possesses the wave nature as well as particle nature, right? So basically, we already knew about light. Light has got the dual nature. Now, as per de Broglie is concerned, whatever we have around us in the universe, every single thing has got the wave nature as well as particle nature. What does that mean? For example, I have got a small particle whose mass is m, right? Let's assume this particle is moving with velocity v. Let's assume this particle is moving with velocity v, okay? Yes. Now people, as I told you, as per your de Broglie's hypothesis concerned, everything, whatever there is in the universe, everything has got the duality, right? Everything has got the wave nature as well as particle nature. Now people, I have got the small particle over here, right? It's moving with velocity v. So as per your de Broglie's hypothesis concerned, there will be a wave associated with this particle as well. There will be a wave associated with this particle as well, right? Okay. And people, what he did was, as per this hypothesis concerned, what de Broglie did was, he basically gave the relation between lambda and the momentum of the particle which will be moving with some velocity v, right? He gave the relation between the wavelength, right, and at the same time the momentum of the particle which will be moving with the velocity v, right? So basically, this lambda, it is the characteristic of a wave, and momentum, this is the characteristic of the particle, right? Okay, I have got a small object moving with some speed v, okay? So there will be a wave associated with this, right? Right? And this lambda, it is basically a characteristic of a wave. And at the same time, if this particle is moving with some velocity v, it has got some mass as well. That means this particle will be carrying some momentum as well, right? Yes. So people, as per your de Broglie's hypothesis concerned, he gave the relation between lambda, which is something which I call as de Broglie's wavelength, which is something which we call as de Broglie's wavelength, right? And this p is something which I call as the linear momentum of the particle. Correct? And as per this hypothesis concerned, lambda, which is the de Broglie's wavelength associated with this object moving with velocity v, it's inversely proportional to the momentum carried by the particle, right? Okay, what is this lambda over here? Lambda is something which we call as de Broglie's wavelength, okay, which is associated with the particle which is moving with some speed v. Okay, what is p? P is something which we call as linear momentum associated with this particle, right? Now people, if I'll remove this proportionality sign over here, I'll get something called as lambda is equal. Lambda is equal. I'll put the constant h divided by p over here, right? This is something which I want you guys to remember first of all. Correct? This is something which I want all of you to remember first of all. First thing, as per your de Broglie's hypothesis concerned, it explains the dual nature of matter. According to this hypothesis, matter behaves like a wave as well, right? Whatever matter we have around us, it can behave like the wave as well, right? And at the same time, let me tell you, the wave nature of the matter was further experimentally proven by the experiment, which is something we call as Davison-Germer experiment. Basically, this is the experiment which you'll be studying in your class 12 optics, right? Okay, but let me just give you the brief idea of this experiment as well. Well, people, there are a lot of phenomena shown by the light, as you all must be knowing, like the reflection, like the refraction, like the diffraction, okay? And if I talk about something called as diffraction, as I'm telling you, diffraction, it's a phenomenon shown by, for example, light. Okay, this is something which you'll be studying in your class 12 optics, right? Let me tell you, this phenomenon of diffraction shown by the light is explained by considering the light to have the wave nature, right? If we consider the light to have the wave nature, then only we can explain the phenomenon of diffraction shown by the light. Now people, what happened over here? How come by means of this Davison-Germer experiment, the wave nature of the matter was experimentally proven? See, over here I'm going to take an electron beam over here. Right? Now people, at the same time, I'm going to make this electron beam to pass through a slit. What you'll be observing, you'll be keeping one photographic plate over here. This is the photographic plate on which image will be getting created. Okay. People, on this photographic plate, if I'll make it like this, if I'll make the photographic plate like this, on this photographic plate, you will see some concentric circles like this, okay? You will see a pattern like this, okay? Basically, this is something which we call as diffraction, right? This is something which we call as diffraction. As I told you, this is something which we will be studying in your class 12 physics, not here. But just let me give you the idea of it, okay? Understand properly what I'm going to say. See guys, for example, this is the electron beam. It's about to pass through a slit. Now, this is the photographic plate on which the image will be getting created. And what you got an image like this. You got these concentric circles like this. Well, this property is something which we call as diffraction. And diffraction was shown by the light, if you remember, okay, which was explained by considering the light to have the wave nature, correct? So this diffraction is explained by considering the light to have the wave nature. So basically this phenomenon explains the wave nature of the light, if you remember. But right here, I took electron beam. I took basically the electrons, right? Okay, so the electron is showing the same pattern as that of shown by the light. So what does that indicate? That simply says your electron, okay, it's showing the diffraction, and diffraction is only explained by considering the electron to have the wave nature as well, okay? So this is how basically de Broglie's hypothesis was supported by something called as Davison-Germer experiment, right? Let me know in the chat box if it is clear to everyone so that I can move on. Let me know fast. Yeah? So people, let me tell you in short what you guys are going to remember. Let's say I've got the, just a second. Let's say I've got the particle whose mass is m. It's moving with the velocity v, right? Remember, everything whatever matter we have around us, okay, which will be carrying some mass, moving with some velocity v, there will be the wavelength associated. There will be a wave associated with this particle which will be moving with some speed, yeah? Okay, and as per de Broglie's hypothesis, we got to know lambda, which is the wavelength of the associated wave with this particle, okay? It's basically equal to h upon p, or instead of p, I'll be writing simply as m multiplied by v, okay? This is something which you all must be remembering for now, correct? Yes? Now people, understand few more important things, right? This is something by means of which your wave nature of the matter was further proven by something called as Davison-Germer experiment, which I told you. I just gave you the glimpse of this experiment. This is something which you have to deal in your class 12 physics in detail. Yeah? Okay. Now people, see, de Broglie associated the momentum of the moving particle with the wavelength of the associated wave, which I told you, right? He gave the relation lambda is inversely proportional to the momentum, and lambda is equal to h divided by p, where h is what we call as Planck's constant, and p is something which we call as linear momentum of the particle, which is basically mass of the particle multiplied by velocity of the particle. Yeah, this is something which you all must be knowing now. Now people, this concept, this de Broglie's hypothesis, it basically gives the satisfactory results for the microscopic particles, right? For example, I'm the macroscopic object. Yes, I'm not the microscopic object. I'm not the microscopic particle, right? I'm the macroscopic object. For example, I've got definitely some mass. Let's say I'll be moving with velocity v, right? If I'll be moving with velocity v, there will be a wave associated with me as well. But that wave will have the wavelength that is going to be negligible, right? So that's why I have given you the statement. This concept is valid. It gives the satisfactory results to the microscopic particles only, not the macroscopic objects. Okay? Right? So remember this thing as well. Correct? Otherwise, this is the marker, right? This is the marker. It has got some mass. Now this marker is moving with some velocity v. There will be a wave associated with this moving marker as well, right? But remember, the wavelength of that wave will be negligible, right? So this concept of duality, it gives the satisfactory results for the microscopic particles like electrons, like protons, like the photons, etc., etc. Yeah? Remember this thing as well. Correct? So people, now let's try to analyze one more thing. Understand properly. See, we got the relation lambda is basically equal to h divided by mv, okay? Let's say I have the particle whose mass is m. It's moving with velocity v, right? It's moving with velocity v, okay? So that means this particle, it will be carrying some momentum that's equal to p, which is equal to the product of mass and velocity, right? If I'll ask you what is the kinetic energy of this particle which is moving with velocity v, you will say kinetic energy of this particle moving with velocity v is basically half of mv square, right? Now people, I'll simply do one thing. I'll just divide and multiply by m. I'll simply divide and multiply by m. So in the numerator, it becomes m square, like this, correct? So can I say something like this? Kinetic energy of this particle whose mass is m, moving with velocity v, is equal to, we know P is equal to m multiplied by v. So m square v square, instead of it, I can directly write as p square divided by what? Divided by 2m. So from this equation, can I get the value of P from here? P is basically equal to under root of 2m multiplied by kinetic energy of the particle, right? This is something which I got. And already we know your lambda, which is the de Broglie wavelength, that's basically equal to h upon mv, or you can write it as h upon p. But instead of p, now what you can use is, instead of p, you can use the term under root of 2 multiplied by m multiplied by kinetic energy of the particle, right? So people, this is one more result in order to calculate the de Broglie's wavelength lambda associated with the particle which will be moving with some speed v, yeah? Let me know in the chat box if it is clear to everyone, right? So the result I have already written over here. Lambda, which is the de Broglie's wavelength associated with the particle moving with the velocity v, is equal to h upon under root of 2m multiplied by kinetic energy, right? Okay, perfect. Let me know in the chat box if it is clear. Fast. So till now I got some relations like this. Let me summarize everything. We got to know de Broglie's wavelength, which is associated with the particle moving with velocity v. It's equal to h upon mv, first of all, or you can write it as h upon p, or people, at the same time you can write it as h upon under root of 2 multiplied by m multiplied by kinetic energy of the particle, right? These are the some relations which I want all of you to take a note of, because from these relations different set of questions are arised, okay? And I'll be showing you the questions in some time, right? So first of all, let me know fast if it is clear to everyone so that I can move on. Let me know fast in the chat box if everything is clear so that I can move on, right? Let me know fast. Perfect, guys. Now let's move on. Let's talk about something interesting now, okay? For example, I have got a charged particle right here, which is at rest. The charged particle I have, right? The magnitude of charge on this particle is q, yes? And I'm assuming this particle right here is at rest. If it is at rest, so its kinetic energy, which is the initial kinetic energy of the particle, right? It is 0 because the particle is at rest, okay? Now, first of all, if I'll accelerate this particle under some voltage V, okay? If I'll apply some voltage V to this particle, right? Because I want this particle to accelerate. If I want this particle to accelerate, I need to supply some potential to this charged particle. I need to supply some voltage V to this particle right here. Then only this charged particle will accelerate, okay? So basically, let me make you understand it like this. See, let's assume this is the positive plate. This is the negative plate, right? Why positive and negative? Because I have connected this with the external source battery like this. Okay, now I have got the charged particle Q. Let's assume the charge on this particle is positive. It's plus Q, for example, right? Now people, for example, the battery is not turned on yet. Okay? So this particle won't be moving towards any of the plates because the battery is not turned on. If the battery is not turned on, there will be no charge on these two plates. If there is no charge on these plates, this particle is not going to accelerate at all. Now, for example, I'm giving some potential difference V. I'm keeping the voltage of the battery as V. Now, what is going to happen? There will be charges on these plates, right? Now, once charges got developed on these plates, I'll say this positively charged particle will start accelerating towards this negatively charged plate, right? This positively charged particle will start accelerating towards the negatively charged plate. I can see that. So the initial kinetic energy of the particle was 0, right? Now, I made this charged particle to accelerate under some potential V. Now there is something in physics called as work energy theorem, right? That's something which you'll be studying in your class 11th physics as well, okay? And as per your work energy theorem is concerned, we say change in kinetic energy right here, change in the kinetic energy of the particle is equal to basically the work done by the external source. Well, the change in the kinetic energy of the particle, which is going to be final kinetic energy of the particle minus initial kinetic energy. Since initial kinetic energy of the particle, so I'll be simply writing final kinetic energy of the particle, which I'm representing by Ke, is equal to work done by the external source. See, the charge present on the particle is Q and it's being accelerated under the voltage of V. So work done by this external source is simply going to be Q multiplied by V, where V is not the velocity, V is the voltage of the battery, V is the potential difference which was applied across the plates. Yeah, right? Now people, you got to know kinetic energy is equal to Q multiplied by V. Few minutes back I gave you the relation lambda is equal to h upon under root of 2m multiplied by kinetic energy. Now instead of this kinetic energy, can I write something as QV directly? Absolutely. So it's going to be h upon under root of 2 multiplied by m. Instead of kinetic energy, I'll be writing Q multiplied by V. This V is not the velocity of the charged particle. This V is the potential difference which was applied. This V is the voltage, okay? This V is the voltage by means of which this charged particle was accelerated, okay? So you got one more relation. Yeah, I want you guys to take a note of this relation as well. There are some questions which are asked whenever a charged particle is accelerated by 5 volts. Whenever a charged particle is accelerated by, for example, 5 volts, what is the de Broglie wavelength associated with that particle? You'll be at that time using this relation, right? This is something which I want all of you to remember as well, correct? Now people, in particular, if I talk about the charged particle electron, if I talk about electron, let's say this is the electron, okay? Let's say this is the electron over here, okay? Now people, I want this electron to accelerate under some potential difference V. The electron is accelerating, okay? So definitely this electron, it will be having the de Broglie's wavelength associated with it as well, correct? And that lambda, which is the de Broglie's wavelength associated with this electron, when this electron is basically accelerated under the voltage V, that is equal to under root of, that's equal to h upon under root of 2 multiplied by mass of electron, multiplied by charge present on electron, multiplied by V, which is the potential difference under which this charged particle, this electron, was accelerated, okay? Now knowing the value of everything, knowing the value of H, knowing the value of mass of electron, knowing the value of charge present on electron, right, we can, after putting all those values into this equation, we get one direct result for the electron, which is basically 12.25 divided by under root of V angstroms. But this result is only valid for the electron. Whenever the electron is accelerated by V volts, okay, whenever the electron is made to accelerate by the potential difference V, at that time the de Broglie's wavelength associated with that electron is going to be 12.25 divided by under root of V angstroms, correct? Let me know fast if it is clear to everyone. Let me know fast. Let me know fast. This is only valid for electron. This is valid for any charged particle which is accelerated under some potential difference, right? Okay. Let me know fast if it is clear. So people, from these equations, directly questions have been asked. And what are the questions asked? Let's talk about those questions. See, I took a charged particle first. I made this charged particle to accelerate under some voltage. And what I'm telling you, change in the kinetic energy as per your work energy theorem, change in the kinetic energy is equal to work done by the applied voltage, which is going to be equal to final kinetic energy, which is Ke, minus initial kinetic energy, that's 0, is equal to charge present on this particle, that's Q. V is the voltage applied. So from here, you get the value of lambda, which is h divided by under root of 2qvm. Yeah? Okay, we have derived this result, if you remember. Correct? Correct. Let's move on, and this is valid only for electron. Sorry, it was not 12.25, it was 12.27, sorry. Yeah, my bad. Okay, this result is only valid for electron when it's accelerated under some voltage V, correct? Yeah? Okay, so let's try to solve one simple question, right? The question was asked once in some competitive examination. It's a very simple and basic question. I'm sure you can easily solve this one. If the kinetic energy of the proton is increased 9 times, so basically I'm increasing the kinetic energy of proton 9 times, yeah? Then the wavelength of the de Broglie's wave associated with it would become. Okay. People, we got to know a few minutes back, if you remember, lambda is equal to h upon under root of 2 multiplied by m multiplied by kinetic energy, right? Let's say I had a proton, right? The proton has the mass n, it's moving with some kinetic energy Ke, right? So its de Broglie's wavelength lambda is going to be equal to h upon under root of 2m Ke, correct? Now what am I doing exactly? I'm basically increasing the kinetic energy of this proton 9 times, right? I'm making the kinetic energy, I'm increasing the kinetic energy of this proton 9 times. So the new lambda, which I'm representing by lambda dash, it becomes h upon under root of 2m multiplied by. Initially, the kinetic energy of proton was kinetic energy normal Ke. Now it becomes 9 times Ke, right? Now it becomes 9 times Ke, correct? As simple as that. Yeah? Correct? Now people, I think it's done. It's simple. It's simple now. If you divide these two equations, what do you get the answer? What do you get the answer? Let me know. This 9 will come as 3 over here. So the new wavelength becomes 1 by 3 times of the initial wavelength, right? The new wavelength becomes 1 by 3 times as that of the initial wavelength. You can clearly divide these two equations. You'll be getting something like this. After dividing these two equations, you'll be getting lambda dash is equal to 1 divided by 3 multiplied by lambda. Or after dividing the equation, you'll be getting it something like this. Lambda dash divided by lambda is equal to 1 divided by 3, right? Okay, after dividing these two equations, you'll be getting this result, which clearly says the new wavelength of the proton becomes 1/3 of the initial wavelength over here. Yeah? Correct? Let me know fast if it's clear to everyone. Let me know. Brian Joseph will be starting that again from Monday, okay? Again, we'll be starting that from Monday. So people, you can let me know if everything is clear till here so that I can move on to the next part. Let me know fast if every single thing is clear till here so that I can move on to the next part. Correct? Exactly. So organic will be resumed from Monday, okay? That's what NEET Aspirant I'm telling you. Organic will be resumed from Monday. मतलब Monday से वापस से organic start होगी. Something is Hindi, yeah? Okay, perfect guys. So now let's try to relate this de Broglie concept with the Bohr's model, yeah? Okay, let's try to relate this de Broglie concept with the Bohr's model. Understand, as per your Bohr's theory is concerned, there was a postulate in Bohr's theory that was MVR. The angular momentum is the integral multiple of h upon 2 pi. I hope you remember this, right? I hope you remember this. And few minutes back, as per your de Broglie's wavelength, lambda is basically equal to h upon mv. H upon mv, correct? De Broglie's wavelength, lambda is equal to h upon mv. So let's try to relate your Bohr's model with the de Broglie's hypothesis. Let's try to relate it, okay? And how we are going to do it, understand. I'll be simply writing it like this. Understand, I'll be writing m, right? Or let's not write m. Let me just take this 2 pi over here. It becomes 2 pi multiplied by r is basically equal to n multiplied by h upon this mv. I'll take in the denominator like this, as simple. Okay, I just did some cross multiplication, that's it. Yeah, I can see something like this. I got one important result. 2 pi r is equal to n multiplied by, instead of h upon mv, I can write lambda. So this is one more result, right? Which clearly says, the electron while revolving around the nucleus, it mainly possesses the wave nature. This is the result which clearly gives us the idea that the electron when revolving around the nucleus, okay, its wave nature dominates. Its wave nature dominates, yeah? As you could see in this relation, we got the characteristic of the wave lambda over here, right? Okay. Perfect. So people, remember this relation. It's very, very simple. So basically, let's assume this is the nucleus of the atom. As per your Bohr's theory is concerned, the electron, as per your Bohr is concerned, electron is a particle, right? Which is revolving around this nucleus in a circular orbit, as per your Bohr is concerned. But as per de Broglie's hypothesis is concerned, this electron, it mainly behaves like a wave, right? Its wave nature is dominating. Right? Okay. Now people, there is one question asked. The number of waves made by the electron moving in a particular shell. For example, the electron is moving in shell number 1. How many waves will be made by the electron? For example, the electron is moving in the shell number 2. How many waves will be made by the electron in shell number 2? Similarly, in shell number 3, how many waves will be made by the electron? Remember, the total number of waves made by the electron made by the electron while revolving is equal to the value of n. Remember this as well. It's very, very important. Okay? It's very, very important. Correct? Remember this thing as well. For example, the electron is moving in shell number 1. Let's assume the electron is moving in shell number 1. So in shell number 1, it's going to make one complete wave, right? For example, the electron is moving in shell number 2. It's going to make 2 complete waves. Similarly, the electron is moving in shell number 3. It's going to make 3 complete waves. So whatever is the shell number, right? Same number of waves will be made by the electron while revolving. And as per your de Broglie's hypothesis, when the electron revolves around the nucleus, right, it mainly possesses what? It mainly possesses the wave nature, correct? Which was confirmed by this equation, right? Let's try to use this equation in the form of questions. Yeah? This is something which I told you, correct? This is something which we got to know. And people, hence wave nature of the electron revolving around the nucleus will be dominating, and the number of waves made by the electron is equal to the value of n. Remember this thing as well, correct? Now there is one simple question which you can clearly solve, right? Okay. I gave you the result right now. Few minutes back, I gave you the result. That was, what was that? MVR, or just a second, guys. Just a second. Okay. All right. So people, look at the question first. In hydrogen atom, if x is the radius of the first Bohr's orbit, de Broglie's wavelength of the electron in third orbit is. Can you let me know its answer fast? The same relation which I gave you a few minutes back, which confirmed that the electron has got the dominating wave nature while revolving. You're going to use that. Can you let me know fast what is going to be the answer of this question? Can you let me know fast? Can you let me know fast? I'm looking at your chats only. Give it a try. Let me know fast. Guys, concentrate on the stuff which I'm giving, okay? Don't deviate at all. Let me know fast. What do you think about the answer of this question? It's a very simple question, guys, yeah? People understand? See, few minutes back I gave you the relation. What was that? That was 2 pi r is equal to n lambda, right? What we are going to see basically, we are going to calculate the de Broglie's wavelength in the de Broglie's wavelength of the electron in the third orbit, right? So I'm going to calculate the de Broglie's wavelength of the electron in the third orbit. So instead of r, I'm going to write r3, okay? Since we are talking about the hydrogen atom, yeah? We are talking about the hydrogen atom, correct? Yeah? For the hydrogen atom, the value of z is 1, correct? And we know the radius of electron in the nth orbit is directly proportional to n square. We know it, correct? Is directly proportional to n square, right? Okay, so people understand. In hydrogen atom, if x is the radius of the first Bohr's orbit, so what is going to be the radius of the third Bohr's orbit? It's going to be n square, that means 3 ka square, which comes out to be 9x, right? Which comes out to be 9x, as simple as that. So it's going to be equal to this n value is 3 multiplied by lambda, right? So this is what 3, 1, this is 3, 3. The value of lambda will simply come out to be 6 pi x, right? This is something which we were supposed to calculate, correct? This is the answer of the question, as simple as that. Exactly, Tushar, you're right. It's going to be 6 pi x. Welcome, Tufal. Welcome to session. Abdul Aziz, Monday I'll be starting the naming reactions because you have been insisting me so long on my Instagram, on my Telegram, so please start the naming reactions. So just for you, I'm starting the naming reactions, okay? Right? So people, let me know, is this question clear to everyone? See, in hydrogen atom, x was the radius of the first Bohr's orbit. So the radius of the third Bohr's orbit is simply going to be equal to 9 times x. That's what I wrote, 9x. N is equal to 3. So from here you got the lambda, which is basically equal to 6 pi x. Yeah? Clear to everyone? Now people, let's move on to something called as Heisenberg's uncertainty principle. What this Heisenberg's uncertainty principle is all about. Understand this as well. See guys, as per this Heisenberg's uncertainty principle is concerned, it is impossible it is impossible to determine the exact position and the momentum of a particle simultaneously as well as accurately. Let me write its statement, then you'll understand it, okay? Let me write its statement. I'm writing its statement as per this principle, it is impossible. It is impossible to determine the position and the momentum of a particle like electron simultaneously and accurately. Right? This is the statement of this Heisenberg's uncertainty principle. So basically, you cannot calculate the exact position and the exact momentum of a particle simultaneously and accurately. If we'll try to calculate the position of the electron, at the same time there will be the error in its momentum. Similarly, if you'll try to calculate the momentum of some particle, there will be uncertainty, there will be error in its position. So both the things, position and momentum, they cannot be calculated simultaneously with 100% accuracy. They cannot be calculated for a particle. Let's say this is the particle, right? This particle is moving with some velocity. I cannot calculate its position as well as momentum, right? I cannot calculate the position and the momentum of the particle simultaneously with 100% accuracy. If I try to locate the position, there will be the error in its momentum. Similarly, if I try to calculate its momentum, there will be error in its position, right? Right? Now people, understand like this. Error in the position is represented by delta x. This represents the error or uncertainty in the position. Error or uncertainty in position, right? Similarly, delta p is something which we call as error or uncertainty in momentum of the particle, right? Similarly, I'm writing a term delta v, which is basically error or uncertainty in the velocity, right? Similarly, if I'll use the term delta lambda, which is going to be error or uncertainty in de Broglie's wavelength, correct? Okay, people understand one important thing over here. Let me make you understand this a bit, okay, more in detail. For example, there is something called as, there'll be something which you have discussed in class 10th as well. There was one question arised in your class 10th physics. How do we see the objects? How do I see this marker? Basically, by using the phenomenon of light, right? By using the phenomenon of reflection, okay, I can see this object. How can I see this marker? Basically, light rays are basically incident on this marker. Then light rays are reflecting back and they are making the image on my retina. Then only I can see this, basically this marker, right? So similarly, if I talk about electron, as per Bohr's theory, electron is revolving around the nucleus, right? We know it, correct? Right? Now people, if I want to locate the position of the electron, if I want to locate this electron, if I want to see this electron, what should I do? Basically, I should put some light which should be incident on this electron, and I am expecting that light will reflect back and I'll see this electron, I'll see the reflected ray, okay, from here, and then I can locate the position of the electron. That's what I'm thinking as per the normal optics reflection is concerned, right? Okay, I'm making the light ray to be incident on this electron and I'm expecting the light ray will be reflecting back and I'll see the reflected ray from here and I'll be exactly locating the position of the electron. I'll be locating the electron basically. That's what I'm thinking. But at the same time, when I'm putting some light on this, right? What is light basically? Light is a form of energy, correct? Light is a form of energy. So basically when light is incident on this electron, can I say electron is going to absorb that energy which is coming in the form of light? And we know if electron will be absorbing the energy which is coming in the form of light, can I say the speed of the electron will change, right? Can I say the speed of the electron will change? So basically I tried to locate the position of the electron, but at the same time there was the error in the velocity of the electron. If there is the error in the velocity, that means there will be the error in the momentum of the electron, right? Because momentum is simply mass multiplied by velocity, right? I'm sure it's clear to everyone. So that's what Heisenberg said. Whenever we try to locate the position of the particle, there will be the error in its momentum. And when we try to calculate the momentum of the particle, there will be error in its position, right? Whenever both the two things, I mean, if both the two things are to be calculated simultaneously, there will be definitely an error in one or the other, yeah? An error in the position I'm representing by delta x, error in the momentum I'm representing by delta p, error in the velocity I'm representing by delta v, error in the de Broglie wavelength I'm representing by delta lambda. Now, he came up with a conclusion with a mathematical statement. What was that? The error in the position of the particle multiplied by the error in the momentum, it's always greater or equal to h upon 4 pi. This is the first statement of the Heisenberg's uncertainty principle. Delta x dot delta p is greater or equal to h upon 4 pi, right? Now people, we know momentum is basically equal to mass multiplied by velocity, right? If there is error in the momentum, the error in the momentum will be due to the error in the velocity because mass is constant, right? Mass is not going to change, correct? I can say the error in the momentum of the electron is basically due to the error in the velocity. So I can say delta p is basically equal to m delta v, right? I can say it like this. Now people, what we can do over here, instead of delta p, you can write m delta v. You can write m delta v, which is greater or equal to h upon 4 pi, right? Basically, the product of error in the position and the momentum is always greater or equal to h upon 4 pi. So the minimum product of error in position and momentum is equal to h upon 4 pi. The minimum product of error in position and error in momentum is equal to h upon 4 pi. That's the minimum product of the two. Maximum can be anything, right? Okay. Now people, I can write this like this as well. Delta x dot delta v is greater or equal to h upon 4 pi m, correct? This is one more mathematical statement as per your Heisenberg's uncertainty principle is concerned. Just remember these two statements. Now we will understand. In the questions, what do we have to do? You'll be given with a question like this. For example, this is a particle. It has got certain mass. Its velocity is, understand, its velocity is, for example, 9 plus minus 2% meter per second. 9 plus minus 2% meter per second. What does that mean? See, it simply means its velocity is going to be 9 plus minus 2% of 9. How much is 2% of 9? 2% of 9 means 2 divided by 100 multiplied by 9, which is going to be 0.18. So it's going to be 9 plus minus 0.18 meter per second. So basically, the actual velocity of this particle can be either 9 plus 0.18 or it can be 9 minus 0.18. So this 0.18 basically is the error in the velocity which is given to me, right? This 0.18 is basically the error in the velocity that's given to me, correct? Yes. Similarly, if I'm writing something like this, I've got a particle, its velocity is 9 plus 0.3 meter per second, plus minus 0.3 meter per second. What does that mean? That means its velocity, its actual velocity can be either 9 plus 0.3 or it can be 9 minus 0.3. So this 0.3 meter per second, this is basically the error in the velocity. This is basically the error in the velocity. Yeah? Correct? Now we will understand. There are a few questions which we need to solve by using this Heisenberg's uncertainty principle. Correct? So according to this principle, the momentum at the position of the electron cannot be determined simultaneously with 100% accuracy. If we try to measure the momentum accurately, error will occur in the position and vice versa. That's something which we know. Yeah? Correct? And these are the two statements which I already gave you. Delta x dot delta p is greater or equal to h upon 4 pi, and at the same time delta x dot delta v is greater or equal to h upon 4 pi m. Correct? There are a few more forms of this Heisenberg's uncertainty principle as well, which I'll be letting you know in some time. Correct? Let's try to do this question first so that you'll just have the idea of what kind of questions are asked from this Heisenberg's uncertainty principle, right? See guys, a particle with the mass 10 raised power minus 10 grams. First of all, whatever relation I'll be using in Heisenberg's uncertainty principle, I'll be using all the values as per SI system. For example, have a look. The mass of the particle is given to me as 10 raised to the power minus 10 grams. So my first point will be to convert this mass into kilograms, which is the SI unit of mass. This is going to be 10 raised power minus 10, right? Divided by 10 raised power 3. So the value comes out to be 10 raised power minus 13 kilograms. I converted the mass into kilograms first. Yeah. If the velocity of the particle is 10 raised power minus 6, just keep it as meter per second, right? Velocity of the particle that's given to me as 10 raised power 6 meter second inverse with 0.001% uncertainty. So the exact velocity of the particle is not going to be 10 raised power minus 6. No. it's going to be 10 raised to power minus 6 plus minus 0.0001% of this value. Correct? Right? What do I need to calculate? I need to calculate the value of delta x. Error in the position, or we call it as the uncertainty in the position. Correct? Now, people, first thing, I'm giving you the mass of the particle, right? Okay. What is this thing? 0.001% of 10 raised to power minus 6. That is basically the error in the velocity. Error in the velocity is given to me as 0.001% of what? Of 10 raised to power minus 6 meter per second. This is the value of delta V. This is the error in the velocity basically, right? Now, what I'll be using? I'll be simply using the relation delta x dot delta V is greater or equal to h upon 4 pi m. Correct? What do I need to calculate? I need to calculate the value of delta x. So you can say delta x should be greater or equal to h upon 4 pi multiplied by m multiplied by delta V. H value, which is the Planck's constant, this is something which you already know, 6.6 into 10 raised to power minus 34. Pi value, you know, 22/7. Mass of the particle is given to me, right, in kilograms. Delta V, you'll be taking in meter per second as per SI system. So from here, you can clearly get the value of delta x, which I was supposed to calculate. Yeah, I'm sure it's clear to everyone, right? Correct? I'm sure it's clear to everyone. Yes? Now, people, understand. Understand one thing. As per your Bohr theory is concerned, Bohr considered electron as a particle, right? Bohr considered electron as a particle, right? This was the nucleus. Bohr clearly said electron is revolving in this circular path, for example. Electron is revolving in this circular path. So as per Bohr, this is the trajectory of the electron. This is the trajectory. This is the path followed by the electron around the nucleus, right? But as per Heisenberg's, is it possible to determine the position and the momentum simultaneously? It's not possible to determine the position and the momentum of the electron simultaneously with 100% accuracy. So can you clearly tell the electron is right now here, the electron is right now here, the electron is right now here, or the electron is right now here? You cannot say that, right? You cannot say that, because it's impossible to determine the position and the momentum of the electron simultaneously with 100% accuracy. In order to tell that electron is here, you should know its position and its momentum simultaneously with 100% accuracy right here. Then only you can say electron is here. Then only you can say electron is here. Then only you can say electron is here, right? But as per Heisenberg, it's impossible to do that, right? So we cannot directly say electron, this is the trajectory of the electron. We cannot say this is the 100% true. You cannot say this is 100% true. Correct? You cannot say the electron is actually moving in this path. The electron at some point of time is here, then it comes here, then comes here, then comes here. No way, right? So basically, as per Heisenberg's uncertainty principle, according to Heisenberg, we can only define, we cannot exactly say electron is here. We can only define the probability of finding the electron around the atom, around the nucleus, right? So we can basically define the probability. We can say electron can be at this position. The electron can be at this position at some instant of time. The electron can be, but we can never say with 100% accuracy that electron is here. Electron can be. So we talk in terms of probabilities from now onwards, yeah? Right? So we talk in terms of probabilities from now onwards. Correct? So according to Heisenberg, we can only define the probability of finding the electron around the nucleus. So this was the reason why the Bohr's model was failed. That this was the major drawback of the Bohr's model. Correct? Okay? Right? Now, people, one more thing. One more form of the Heisenberg's uncertainty principle. What is that going to be? See, the first form I gave you in terms of delta x and delta p. The second form I gave you in terms of delta x and delta v. The third form I'm going to give you in terms of delta x and delta lambda. And how we'll be deriving it. Understand? First of all, we know lambda is equal to h upon p. This is something which we all know, correct? I'm going to differentiate this lambda with respect to p. So it becomes d of lambda divided by d of p will be equal to. After differentiating it, it will be minus h upon p square, as simple as that. Yeah? Correct? What does this minus sign tell us? This minus sign tells us simply on increasing the momentum, wavelength decreases. On increasing the momentum of the particle, the wavelength decreases, right? Okay, this is the significance of this minus sign over here, correct? What is d lambda? What is dp? So first of all, I'm going to replace this d lambda and dp by delta lambda and delta p, okay? And this minus, I told you the significance of this minus sign, so I've got nothing to do with this minus sign over here. So from this relation, can I get the value of delta p from here? Can I say delta p is basically p square multiplied by delta lambda divided by h, correct? Delta P is basically P square multiplied by delta lambda divided by H, correct? Already, we know the relation. We know the relation delta X dot delta P is greater or equal to H upon 4 pi, correct? So people, I can say delta X dot, instead of delta P, I can put this value, which is P square multiplied by delta lambda divided by H is basically greater or equal to H upon 4 pi, correct? Now do a bit of cross multiplication. You get delta X dot delta lambda greater or equal. H multiplied by H means H square divided by 4 pi. This P square comes in the bottom. This 4 pi P square, right? Okay. Now people, few minutes back, I told you one relation. Lambda is equal to H upon P, correct? Or you can say lambda square is equal to H square upon P square, right? So instead of this H square upon P square, I can directly write lambda square, correct? So I got one more form of this Heisenberg's uncertainty principle, which is delta X, which is the error in position, multiplied by error in de Broglie's wavelength, is greater or equal to H square by P square means lambda square divided by 4 pi. This is one more form of the Heisenberg's uncertainty principle in terms of what? In terms of delta lambda and delta X, right? No, Mustaqim, I do not read the chats often here. Let me know fast if everything is clear till here, right? This is one more result. This is one more result which I want all of you to take a note of directly. Perfect, guys. Exactly. Let's move on. So this is the result which we derived just now. Delta X dot delta lambda is greater or equal to H upon 4 pi, correct? Now people, this is one question, right? Let's try to solve this question. It's a simple question, but you need to be careful with certain things, right? You need to be careful with certain things. Understand? First of all, an electron is accelerated from rest by applying a voltage of 6 volts. So I'm applying a voltage of 6 volts to the electron, right? Delta X, error in its position, uncertainty in its position, it's given to me as 7 divided by 22, right? Nanometers. Then delta lambda will be. I need to get the value of delta lambda. This is in nanometers, right? This is in nanometers. Right now we derived one equation that was delta X dot delta lambda is greater or equal to H square. It was not H square, it was lambda square, right? Lambda square upon, what was it? What was the equation which we derived? Just let me have a look on it. What was the exact equation which we derived? It was delta X dot delta lambda is greater or equal to lambda square divided by 4 pi, right? Lambda square divided by 4 pi. Okay, lambda square divided by 4 pi, correct? Your delta X dot delta lambda is greater or equal to lambda square upon 4 pi. This is the relation which we derived few minutes back, correct? Now people, understand. Voltage is given to me as 6, right? So first thing, can I calculate the lambda over here? As I gave you the relation in the beginning, when the electron is accelerated by some voltage V, lambda is equal to 12.27 divided by under root of V, and the value comes in angstroms. When you will clearly solve this, you will get the value something as 5 angstroms. You'll be getting the value as something as 5 angstroms, something like this, right? So 5 angstroms, I can write it as 5 multiplied by 10 raised to the power minus 10 meters. Correct? Now the question is almost done and dusted. Yeah? See guys, what do I need to calculate? I need to calculate the value of delta lambda. Can I say delta lambda should be greater or equal to lambda square divided by 4 pi multiplied by what? Multiplied by delta X. Correct? Lambda value we have, 4 value we know, pi value we know, delta X value it's given to us. So from here, can you calculate the value of delta lambda? Absolutely, you can do that. Yes. From here, you can calculate the value of delta lambda, which I was supposed to calculate, and you can clearly do it. Yeah? Right? Perfect? Exactly, guys. So finally, you get the answer of the delta lambda as 6.25 into 10 raised power minus 11 meters, right? Okay. So I just gave you the procedure of how to solve this question. Now it's your turn to do the calculation part and get the answer. Yeah? Now we will one last question. With this, we'll be ending this, and in the next session of atomic structure, we'll be starting with the quantum numbers and the quantum mechanical model, right? This is one more question which I want all of you to take a note of. If the error in the velocity and the position are same, So as per this question is concerned, error in the velocity, which I represent by delta v, and the error in the position, which I represent by delta x. Error in the position and the error in the velocity both are given to me as same. What do I need to calculate? I need to calculate the error in the wavelength. Delta lambda I need to calculate, right? Should I be giving you this as the homework, right? Should I be giving you this as the homework, or you want me to solve it right now? You want me to solve this question right now, or should I be giving this question as the homework? Let me know fast. All right, I'm giving you this as the homework, right? Do let me know the answer of this question in the comment section afterwards, right? Okay, so people, with this, your de Broglie's concept, your de Broglie's duality, and the Heisenberg's uncertainty principle, that's over. The next session of atomic structure is going to be your quantum numbers and the quantum mechanical model, right? That is one of the most important topics from the chapter atomic structure, right? And if you have any sort of questions regarding this, you can let me know the questions in the comment section, yeah? So with this, I end the today's discussion here, right? And people, if you have not enrolled into the actual Vedantu classrooms right till now, do that as soon as possible, okay? We have got some 3 plans for you, and on every plan, you do not have to pay them amount in one go. You can pay this much of amount in installments as well, yeah? Okay? And at the same time, if you are new to Vedantu, you have no idea of how the actual Vedantu classrooms look like, what you need to do is, you can give it a try for a month, right? Vedantu has created an option like that as well, okay? You can take the pro subscription for a month, and this is the pro subscription fees which you need to pay for a month, right? If you think you are getting benefit out of the sessions, then go for the 2-year classroom program, and the entire fee of 2-year classroom program is not going to be paid in one go. You can pay it in installments as well, like the monthly fee, yeah? Okay, and while enrolling, I mean, there's a link in the description box of the video as well. Do click on the link, right? After clicking on the link, you need to use the coupon code as WSPRO, and after using this WSPRO, you'll be getting some 30% discount as well. There is one more link in the description box of the video, that's for the Telegram. Do click on the link, get added to the Telegram group, and stay updated about the classes. And the ones who have not liked the video yet, please and please do like the video, share the video with your friends, and do not forget to subscribe to the channel as well, right? Okay. Well, people, tomorrow there won't be any session. I won't be taking any session tomorrow. I'll be taking the session day after tomorrow, right? And day after tomorrow, most probably it's going to be the quantum numbers or the quantum mechanical model, right? And from Monday, for the NEET 2021 students, we'll be starting we'll be starting the naming reactions, right? From Monday. Okay, so with this, I'll take a leave here. The ones who have not liked the video, please do like the video, share the video with your friends, and do not forget to subscribe to the channel as well. Okay, I'll see you guys day after tomorrow. Till then, you guys take care. Bye-bye. God bless you all. Love you all, and see you soon. No, Tushar, I do not watch that. Yeah. Okay. Perfect, guys. See you. Bye-bye.